now move to the Industry Forum discussion on semiconductor manufacturing and OSAT. Venkata Simhadri, the General Chair of the VLSI Design Conference, will be the organizer of this session. Mr. Venkata Sudhakar Simhadri is a serial entrepreneur and a proven executive in the semiconductor industry with 30+ years of experience. He was the founder, president, and CEO of Gigacom Semiconductor LLC and founder and director of Gigacom India. Both of these companies were acquired by Moschip. Earlier to Gigacom, Venkata was the founder, president, and CEO of Time to Market TTM from 1998 till its acquisition by Cyient in 2008. Mr. Venkata is currently the MD and CEO of Moschip Technologies Limited, a member of ISA Hyderabad chapter, and the brains behind the ISA AI Summit started in 2021. With that, let me ask Mr. Venkata to please come on the stage and moderate the session. Thank you.
Thank you. Thank you for the kind introduction. So we all know that this conference is more focused on VLSI design and embedded systems design. But right now, India is going through a revolution. The manufacturing has become a key topic for the whole country. We know that the Indian government announced a $10 billion package, and majority of it is focused towards the manufacturing side of things. So with that in the background, I felt it is very important for us to at least have a focused session on manufacturing as well. And that is the reason I kind of, chairing this small forum here and put together some very important topics, interesting topics, as well as a panel discussion. And as the first keynote speaker in this forum, I invite Tushar Dayagude from Transform. So Transform is one of the leading gallium nitride fabs in the world. And Tushar works as a worldwide sales head, and he has been partnering with Moschip and PowerX to bring some advanced power management solutions to the country. And with that, I invite Tushar Dayagude onto the stage.
Good afternoon, everyone. So, we have been working in India for the last few years. And instead of just presenting a topic or technical details, wanted to show actually what we have done. And we'll get back to that at the end as well on what our roadmap is. But with the help of Moschip, Venkata, our silicon partners, Selana, who will also present later, and new startup company called PowerX, we actually designed, developed, and manufactured a complete USB-C charger, which is a very advanced charger made here actually locally in Hyderabad. So with that backdrop, I want to introduce Transform GaN, its comparison with other power semiconductors, and see how we can make India more self-reliant and efficient in these power systems. So I think this presentation is a mix of technological advances in power semiconductors, as well as for some of the experts. I don't want to go into circuits. That if you want to talk about circuits or see some other demos, we have a booth here, the Transform booth, along with PowerX. So I'll introduce GaN applications vis-a-vis other power technologies. Talk a little bit about where GaN applies from, all the way from 30, 40 watts to 10+ kilowatts, including adapters, computer power supplies, PV solar inverters, 2, 3-wheelers, as well as automotive and UPS. A little bit about the company. Then I'll compare Transform GaN with other power semiconductors, and then we'll give you an overview of systems that are enabled by Transform GaN. And we do have a few customers who do some design work in India, but this has truly been our first foray into India. Most of the other adapters are either designed in China, manufactured in China, or in Taiwan. So I hope with this we can get India onto the bandwagon of not just manufacturing. Like India manufactures a lot of iPhones, but we can actually design the components, develop everything here, and do it not only for India, make in India, design in India, and sell it in the world. So GaN is the future of power electronics, power semiconductors. Silicon, as they say, it's an old technology, it's a reliable, proven technology. Silicon carbide is coming very strong in automotive and high power. And then if you want to make the power systems very efficient, smaller, lighter, and actually lower cost, GaN is the material to adopt. And again, I don't want to make parallels between other countries, but China has adopted GaN in an extremely widespread manner in all their applications. So I think this is a good time for us to catch up, not only catch up, but be on par with the rest of the world. So again, I promise that I won't make it very technical, but just to see where GaN plays. GaN plays in the high frequency, domain where power density and efficiency are critical. That improves, they call the figure of merit in power semiconductors. So this is where GaN actually, and what does it mean for India in terms of power savings? So in 2025, we believe that moving to GaN in adapters, electric two-wheelers, four-wheelers, and other power supplies, we can save about 1.1 terawatt hours of energy that will supply about 2.6 million rural households. And if everything had moves to GaN, by 2030, the annual savings could be about 150 terawatt hours, which is actually enough to supply all of the rural households. So GaN is now getting very pervasive in everything from the wall adapter to automotive. And I will talk about each of these as we go along. So, fast chargers, servo motors, PC gaming, all these things. The old technology was MOSFETs, IGBTs, BJTs. They are migrating to GaN as well as silicon carbide devices for high power. It will be unfair to not talk about the ecosystem. So Transform is a dominant player, but not the only player. But we have the widest portfolio of products that can work all the way from all the applications that I just talked about. So the founders, one is from Bombay IIT, one is from Kanpur IIT. Professor Mishra is kind of the father of the GaN devices. I'm very fortunate to work with them. And we just opened an India office, and also we have a very strong partnership with Moschip over the last few years. So Transform owns its own GaN wafer production supply chain, all the way from designing the GaN devices to EPI, which is the core manufacturing process. And then we have a joint venture fab in Japan. We are looking at bringing some of this technology to India, as well as working with Venkata on some of the other initiatives, including OSAT and system level solutions. Our GaN FETs are now into all the markets here: adapters, data centers, crypto, industrial, aerospace, and automotive is the next big one for us, especially starting with the two-wheeler, three-wheelers. I've spoken with almost every scooter, motorcycle manufacturer, and they're all hungry for getting the OBCs made from GaN. So the market opportunity for GaN worldwide, as of last year is about $1.8 billion, getting to about $6 billion. And if we can get into the traction inverter for automotives, like for Tata or Mahindra, that could balloon to about $15 billion worldwide. And not just that, this is just the GaN component, but you also have controllers, DSPs, FPGAs, and of course the mechanicals, PCBs. So that ecosystem could be close to about $40 billion. So this is again, a very, very good market for India to participate in. It's almost like, not going with the, telephone line and going straight to 5G. So I think India can actually, embrace this much faster. Growing opportunity in EV, like I said, OBC, inverters, EV powertrain, and I think the big opportunity also in two-wheeler, three-wheeler. I can go in more details in that as well. This is a kind of a eye chart on how GaN competes with other devices, and especially the transform GaN. But I think let me go to the next slides because those are a little more, yeah. So GaN has enabled kilowatt class power supplies for servers. HP, Dell, Facebook, Amazon, Microsoft. They have started now going towards GaN power, and India with its huge potential for data centers, I think will have a policy for what they call as a titanium rating or platinum rating, so that you can reduce the overall power consumption of the country. We are into all kinds of hardware. Corsair, that's a gaming power supply. AES, that's a aerospace power supply. TDK, some medical devices, as well as the computing devices. So GaN is a power semiconductor. It comes in various packages, and of course then it's bundled with the controllers, the PCB, everything to make the whole solution. But this is the enabling device, and these are the packages we are in. So all the way from the 30 watts to 250 watts, all the way to about 10 kilowatts. And then when you parallel them, you can make it multi 10 kilowatts. So in comparison with silicon, that's the current state, is simpler to use an interface and makes systems smaller and efficient. Next slide. In comparison to silicon carbide, again, they are much simpler to use an interface and make them smaller and efficient. And then with respect to other GaN, we are, like I said, we are not the only GaN company. There are other GaN companies, but make it higher reliability as well as the same, more efficient and simpler to use. Again, this is more for some of the academics. We do a lot of work with the end customers in terms of their application. So whether it's power adapters in this category of 65 watt, there are various power categories, there are various applications or end applications, and then in power supplies they call it the topologies. So there are various topologies. I think Silana is going to talk about one such topology in the later sessions. So it's a bit of a complex field. There are controllers, DSPs, microcontrollers that are used to make the whole system. So we will work with customers and enable them. I'm just going to give a brief summary of some of the power supplies that we are into. And this is where, again, all these are used in India. They're mostly kitted from China or maybe Taiwan, and then probably assembled here, or just end products are sold in the Indian markets. So this is an opportunity for us to work together and make this a reality, not only from a manufacturing perspective, design perspective, but also from a power savings perspective. So these are some of the adapters and chargers that you probably see on Amazon or Flipkart. We are one of the dominant players in those, from 30 watts to 240 watts. So the one that we have is a 65 watt 1A 1C, and I'll talk a little bit more about that. But we are trying to put India into the game, whereas all these have mostly, I believe, mostly have come from China. Again, I don't want to get into the details of these solutions, what is there inside, but they are pretty intricate. They are in a very small form factor, and a lot of electronics is packed there. So it's, it looks small, but it's pretty complex. And the reason why is it is complex, it's pretty multidisciplinary. You have to do a good IC design, you have to do a controller design, you have to do a processor design, you have to do protocol software, and pack it into a very small system. So to get the right kind of efficiency as well as the industrial design possible. So again, I don't want to get into the details of these systems, but I just want to show how complex some of these systems can become. And again, from 70 watts to 360 watt, the systems get more and more complex, and you have more and more options on how to address them. So we have more designs in the pipeline, and we will work with Indian companies. We already have, demonstrated that with one partner company, but we will bring, more products. 65 watts was the first one, 100 watts, another one. Next slide, please. 250 watts for computer medical power supplies. 330 watts to 800 watt platform for telecom and servers. And again, these are all best-in-class solutions. They are not just going to be made in India, but they'll be world-class solutions made in India for the world. I think another topic of a lot of interest in the country itself is the powering of electric 2, 3, 4-wheelers with GaN, all the way from 300 watts to 30 kilowatts. And when I say 30 kilowatts, it's not for the two-wheeler. It's mostly for the battery charging stations like Gogoro, where people can go and swap the batteries. So there are various types of categories. There is portable chargers, there is a fixed chargers, then there is battery swapping, as well as what they call as the pole chargers or fast chargers. So in all of this, GaN can make the solution smaller and actually reduce the losses by 50%. And inadvertently, because of this, you will make the system also cheaper. So one of the things that when I talk to Indian customers, they say, is GaN very expensive? And unfortunately, GaN was expensive a few years back because it was a new material. So the volume was not that great. But now, over the last 2-3 years, GaN has become, at least on a solution level, on par or lower cost than its silicon counterparts. So we, again, can work in every relevant power conversion segment and bring very world-class solutions, to this market. So this is one of the architectures for a battery swapping station, where you have 10 kilowatts to 30 kilowatt power level. It can be either a pole charger or a battery swapping. So this is one solution that we also have worked on. We are actually developing a 750 watt OBC. One of the reasons why the market in India is actually taking off is I don't need to tell everyone here, why the two-wheeler, three-wheeler, electric two-wheeler, three-wheelers are taking off. Low noise, low pollution, and reasonably easy to operate. But one of the reasons why the penetration has not happened as fast as it should is because it's also missing what is called as an onboard charger. And we are working with companies to develop a complete OBC, onboard charger, with power delivery, charging electronics, and battery profile management that can reduce the size by about 20% and 30% lower on the losses. So a sample of this assembly is actually there in our booth. So if anybody wants to look at it, welcome to come and visit us there. We will be sampling this part by, end of March. And so, again, this is another full design that is designed, developed, and will be made in India. And India is one of the largest markets for two-wheelers, three-wheelers. It's also a protected market. Sometimes we may not make the best products, but we protect it. So, it doesn't matter, either way, we'll take advantage of that. Okay. Yeah, and last but not the least is the UPS systems, UPS and PV systems, which are, again, getting a lot of traction in India. So GaN will allow them to make it smaller, cheaper. Same thing, make it higher frequency, make it lower cost, make it higher power density. And, instead of having what is called as a 2U size, you can put it in 1U size. Again, these are huge market opportunities for India, to kind of leapfrog some of the existing power electronics and move to the next phase. There's another slide to show all the applications of, GaN in the electric vehicles. So we are also working with some of the electric vehicle companies. One of them starts with T, one of them starts with M. You know who I'm talking about. So, okay. So with that, next slide. So, I really want to thank, our partners here, Moschip and Silana for doing a fantastic job in, getting this whole system. It took, I would say, 2 to 3 iterations. It was not a simple design. So in China, people started developing GaN adapters probably in 2017, 2018. And it took about 3 years for them to start penetrating the market. From 2020, you could see GaN adapters in the market. But actually, I think within a year, this design from inception to complete delivery of the whole, package, I'm really, proud, that, we have accomplished this. And I think there are more, such designs on the way. And, again, the thing is, Indian conditions, for the power supplies are slightly unforgiving. So, in terms of compliance and safety, right, we had to make sure that they don't burn out like the Chinese counterparts. So again, with that, this is, I think, is a very good accomplishment. So Venkata, I want to invite you, to showcase this. So again, this is not the only thing that we'll be doing. We will be doing, more, advanced power systems here. Lighting is another one, especially connected lighting. We have some work going on with another large company. It starts with R and ends in E. So you probably can guess the name. Two-wheeler, three-wheelers, as well as inverters and UPS systems. So with that, I would like to conclude my talk. Next slide, last slide. So all I want to leave the audience with one message, Indian companies should really adopt GaN as soon as possible and produce world-class, cost-effective systems. I think this is a good opportunity because we have not taken advantage of the existing solutions. So let's leapfrog everyone and go to the new solutions. Just like China did. They didn't build any wiring infrastructure for cell phone for the phones. They went straight to 2G, 3G, 4G. So I think this is a good opportunity for us. So with that, I would like to thank everyone for listening to the talk. Thank you.
Thank you, Tushar. Thanks for taking the time and fly from all the way from California to educate us on the GaN. So GaN is going to be a game changer for India, I believe. Tushar, please, 1 second. So, and a lot of times we think designing a 3 nanometer chip is the most exciting thing. Trust me, every 5G base station that is installed out there, it needs power supply, and GAN can be a game changer for us. With that, I invite Satya Gupta to give a memento to Tushar.
So I think Tushar and Venkata has laid out the advantage of the GAN, and I think lot of innovation in product space can be done by all of you. You will get the lure of using a Chinese GAN chip. Don't fall for it. Talk to me, Venkata or Tushar. We have been working with the transport team for more than 1.5 years. Anybody wants to do a GAN product, please get in touch. Don't use the Chinese GAN chip.
Thank you. Thank you, Satya. What Satya is saying is if you see a PowerX product on the Amazon, and which is like 500 rupees more than the Chinese product, please buy Indian product. Right, Satya? Thank you. So we are running a little behind, and we have another exciting speaker next. So people keep saying that, India doesn't have fabs, we don't have this, we don't have that, no manufacturing here. But trust me, there is a fab in Hyderabad. And this is a gallium arsenide fab. It is owned by the Indian Defense, Government of India. And I like to invite Mr. Anant Naik, who is the CEO of GATEC. This fab is very close to the Hyderabad airport. And they are actually manufacturing some old class gallium arsenide products. And these are, going into some very critical missions for the Indian defense and aerospace. So Anant Naik is an IIT Kharagpur graduate, and he also has a master's from University of Mumbai. And he has been the CEO of GATEC, and again, he is from Hyderabad, and this fab is in Hyderabad, right in our backyard. Not many people know about it, so let's hand it over to Mr. Anant Naik. Give him a round of applause.
I'm thankful to Venkata Simhadri for inviting and making this a very small industry session among the VLSI designers. And ours is a 3-5 compound semiconductor fab. And we have our own PDKs, our own design centers, and our own fab line and product development. We are not right now open to the market today, but it is a strategic application fab, and we cater to most of our output goes to ISRO for satellite applications and DRDO for EW and radar applications. So I will just like to take this opportunity to introduce you to GATEC and what kind of products we are making, and there is a big opportunity ahead in this direction of compound semiconductor also. And silicon is way ahead in design as far as India's output is concerned. Most of the design centers from world-known fabs are in India, Bengaluru, Hyderabad, and for that, I think this is a slightly different area compared to that. So recently, because of the pandemic, we all know of the supply chain issues. Then a lot of tension between US and the Taiwan, and most of the time, all the countries had a lot of challenges with products which depend on the semiconductors. And we know that a lot of pressure on Taiwan because they have the foundry TSMC, which almost 50+% of world over deliveries of silicon ICs, memory chips, and processors are supplied through Taiwan. So we need to have a foundry in India, and that's why the government of India has come out with an aggressive plan, and they're pumping in 76,000 crore rupees to begin with this, and this is not the first time. There will be a couple of more such tranches coming over the period of time. So maybe all the foundries working in India for design should also try to work with some Indian partner and set up a foundry, which can, like after maybe 5 to 10 years, it will start generating a lot of profits. India is a big customer, big user, and a big design center. For GATEC, we have an ecosystem. We have a design and technology development at solid-state physics laboratory, which is in-house is a DRDO laboratory, and that is the technology goes to production when it comes to GATEC. So most of the time we do it concurrently and implement it for the production at Hyderabad. So let me introduce briefly what is an MMIC. It's a monolithic microwave integrated circuit. The density is nowhere near to the silicon-based ICs, but the application is in area of to terahertz level as of today, and only the material. Silicon is also catching up in the way of silicon germanium-based RF ICs, but the power levels are not much. And as in the previous talk, it was mentioned, gallium nitride. Tushar has mentioned about the application on the DC switching side and commercial applications. But gallium nitride also finds a huge application in RF segment. And that caters to all these radar system as well as EW systems and communication systems. So an MMIC is okay, so you can see a wafer, and you can have around 150 or 300 MMIC chips on it, and that actually goes into radar, satellite communication, and ISA radar, which is latest radar technology for fighter craft. Our LCA using ISA radar technology, and ground-based radars for tracking and air defense radars, for example. So MMIC is functionalized by designing a module. A solid state, say for example, I am putting up 2 modules as an example. IC goes into it, and it is made functional by way of solid state power amplifier or a trans receiver module. So these are 2 products of GATEC which are used for space applications, and that I will briefly say. And this one TR module is the one which was used in the recent launch of ISRO satellite we know EOS-4. We call it as a RISAT 1A. And that is made, the chips are made at GATEC. The modules are assembled, tested through private partner, but qualified by GATEC. And it is now flying in the space and giving good results. Each satellite requires around 10 to 11,000 MMICs. So right now we may say very easily that we have got 50, 60,000 MMICs flying in this space. Made in India, modules made in India, designed in India. So just to compare the market, like there are gallium nitride as well as gallium arsenide. Gallium arsenide is a precedent of gallium nitride. Gallium nitride is taking the market by storm because of its power efficiency and power handling and the ease of design, and the chip size is smaller than the gallium arsenide. So, but however, gallium arsenide is still not losing the competition because there are certain niche applications that can only be met by gallium arsenide. And this is the market yield report which shows that gallium nitride will have almost 21% of CAGR, whereas the gallium arsenide will still progress with a moderate CAGR of 3.1%. You can see the defense market for gallium arsenide is not changing. So we are a gallium nitride as well as gallium arsenide foundry. And whereas the gallium nitride is increasing very fast in defense sector also. And as we know, semiconductor ecosystem, what does it mean? Anyway, we are all working in the same area, so that it covers five equipment, chip design, for processing, then embedded application software, we also need a lot of raw materials, and these are the challenges for India as of today to set up a foundry. But with the help of government and all the planners, I think slowly at down 4, 5, 6 years, we will start getting our own raw material as well as equipment support team established by the vendors, OEMs in India to cater to these fabs which will be coming up as well as the existing fabs. So as I said, we have many design centers in India. Fab-wise, India is having a moderate application, 3-5 application. Because of the strategic requirement, we initiated this around 28 years ago, and we are trying to overcome the restrictions that are put in by the countries which are holding these technologies. So we work on a model called IDM. Means we have our own product design team and we make our own products, as well as we offer the foundry service as a pure foundry to our users in ISRO and DRDO. So we have got design centers at these units of ISRO as well as DRDO, and they design on our PDK, and then we load it on the foundry and then supply, qualify the product and hand it over. So this is how we function. Right now we have got 0.7 micron to 0.13 micron technology, and now we are actually entering into 80 nanometer technology for compound semiconductor. These are some of the tools that are required. This is unlike semiconductor tool. This is electron beam lithography, then reactive ion etchings are involved, then plasma enhanced deposition systems are involved. The processes are completely different than the silicon fab. So this our setup is available at GATEC, Hyderabad. And these are on wafer RF testing tools. That is required because when you process a wafer, you have to monitor the wafer progress over a period of time. You need to monitor all the performance parameters for the wafers that are being processed, and we have to qualify them. Then only it can go ahead. So these are some of the tools which has a high power load pull system and low noise noise parameter measurement system. They're all in-house at Hyderabad. Next. Then we also have a set of reliability tools because you need to qualify this for space. And there are very, very stringent requirements for space applications. And the device has to pass through 2,000 hours of storage tests and burning tests at elevated temperatures. And once the product is clear, then only it is handed over for space application. Because you cannot go above and repair the system. So once it is gone, it's gone. So this has to go through a very rigorous quality and reliability cycle. So this is some of the technology that I'll just try to depict it because 15 minutes time is not sufficient to go into all details. These are very complex technologies. So we have got mushroom gate technologies. Now we can say that the picture in the bottom, you can see 0.13 micron for feature which is making a gate and very big mushroom stretch above it for reducing the parasitics. So this kind of technology is already working at SN and products are being delivered by GATEC. Next. So right now we are into 80 nanometer and 35 nanometer feature development for active transistors. So maybe in next couple of year or so we'll have product out of it. When GATEC says product, it's a qualified product. We do not go by the demonstration of a circuit because most of these devices are already demonstrated. But once we qualify it through rigorous this thing, then only we give it for display it as a product. Next. Now these are some of the technologies and products. Just now I mentioned about the products and technology. This we are also into laser diodes, semiconductor laser diodes for some of the applications in directed energy weapon possible. Right now we are not using it, but we are developing for that. And so there are a lot of application areas in RF field, like broadband amplifiers, narrowband amplifiers, limiters, oscillators, multiplexer, mixers. So all these are now available from GATEC Foundry, which are a qualified product designed by us. And as of today, we have got more than 150 IP, design IPs and product IPs, and many of them are space heritage ICs. This is some of the examples I'll say. This is phase shifter integrated circuit, which is heart of any radar, electronically scanned radars. Without that, you cannot scan the radar and detect the incoming, intruding aircraft or a missile or anything. So this is developed by us for L-band applications. Next. And this is, we are also working for a project by DRDO Anvesha, which is space-based product. And our systems are going into that also. These are a collection of some of the products which have gone into ISRO applications, which is Chandrayaan-1, RISAT, 1, 2, and now 3 also we are giving the products. And all TES, Cartosat, TETSat, and most of the communication band satellites. So any data link or a communication download, upload speeds, all through this MMICs are happening. Here there is no silicon chip because these are already radiation hardened material. So it can very easily go to space. Next. So this is one more satellite which is likely to be, I think one version is already launched by SRO, and the second version will be coming in less for a couple of months. Next. Now, this one example, what we can have when we have our own indigenous technology. For example, the earlier series satellite, we have the top row, we have that TR module, which was quite bulky and which was used in RISAT-1, which was launched in 2004 or 5. This worked for almost 7-8 years, and right now, the satellite is no more in the space, but we supplied another version, that is the second line, which is a LTCC based, which has reduced the weight of the panel by almost 150 kilogram weight. So that actually for a space application, the reduction in weight is a prime requirement, so that your satellite can, or the rocket can carry additional payloads. The last one is a core chip, for C-band core chip. Now the complete top line is made into a single integrated circuit. That will actually reduce the weight by almost 1/4 of the original weight of the satellite. This has been now next generation satellite will use this MMICs. Now coming to the gallium nitride part, I think Tushar has given a lot about the reliability, power efficiency of gallium nitride for commercial applications like charger and DC-DC switching and other things. But for RF side, we have a gallium nitride technology. We have the PDK up to X band, and we have 0.25 micron gate length transistors, and now we are into X band MMICs, as well as the power bars, which are very high power, 130 to 150 watts power out from a single transistor, which can further be combined into a kilowatt level of powers also. Next. And there is a very wideband, 5 to 18 gigahertz wideband core chip. This technology absolutely restricted. Nobody can give it to India because it has a very significant EW applications. This has been developed and designed by us, and this has been demonstrated for actual applications. And it is actually a lot of many MMICs into a single IC. You can call it as a system on chip for a kind of a system. But when it operates at a gigahertz frequency, the design becomes very sensitive and very difficult. And this is similarly a very technically competent product for our defense electronics laboratory. And this is called wideband bidirectional amplifier. So in any ISR radar, there is a transmit signal, there is a receive signal. The signal tend to drop in between. So this IC cater to amplify the signal which is weakened during the operation. So in both the directions this works. So it will be a bidirectional amplifier. This is also qualified and fabricated by us. And this is same thing. This is a gallium nitride based core chip. So TR chip. This is designed and developed at GITEC. Next. Now finally, we have gotten our internal molecular beam epitaxy system also that we are using for developing a terahertz. Now terahertz and quantum technologies are the things in future, and you will see a lot of publications and products out of these two technology range, terahertz as well as So we started working on that, and we have a detector diode for terahertz, which is right now we are targeting through 3 terahertz technology. Right now we are demonstrated up to 2.3 to 2.5 terahertz device, and now this PDK is available for designing mixers and other circuits out of that this technology. We can see a very difficult technology called air bridge interconnection technology, which was evolved in-house, and these are some of the device and device configurations for terahertz. Next. Okay, thank you very much.
Thank you, sir. It's a wonderful presentation, and give him a big round of applause. And we all should be proud that there is a real fab sitting, right in our backyard and doing some of these products that are really putting our satellites and into the orbit and powering our missiles. So with that, I invite Srini Bairi to give a memento to.
Next, we have a panel discussion on semiconductor manufacturing in India. We already have Venkata over here who's going to be moderating the session. I would now like to call upon the panelists on the stage. Mr. Suraj Rengarajan, CTO Applied Materials. Mr. Harpreet Singh Jatana, SCL ISRO. Mr. Anand Muttaya, VP TESOLV. Mr. Devesh Trivedi, India Site Head Global Foundries. And Mr. Brahmanand Reddy Patil, Managing Director, Vector Informatic. With that, I hand it over to Mr. Venkata to take it forward.
Good afternoon, everyone. So this is an interesting panel discussion, and we have some eminent people from the industry who are with the manufacturing background here. So I'll quickly go around the team and introduce them. We have Anand Muttaya here. He's from graduate. He is a graduate from University of South Florida, and he has 25 years of experience in semiconductor industry, and he worked at companies like Cyrix, Intel, and mostly in the test engineering side. And when we talk about manufacturing, testing is one of the key components in there, and he brings in a lot of experience in the test side of things. And he is currently working for TESOL Semiconductor as VP of Engineering. And then we also have H.C. Zatana. He is, he retired from Semiconductor Complex Limited. As I said, we keep complaining that India doesn't have fabs. In fact, SCL is the first semiconductor real fab in India, and it is still operational and producing chips. And Mr. Zatana will give a little bit more information and details about it. So he's a former scientist G and group director, and he's a design and process group at SCL. It's right now part of Department of Space with the Government of India. And he led a team of 78 scientists and recently retired from SCL. And his key achievements during the last 8 years, he indigenously developed an SOI CMOS process at SCL. And he's involved in the development of high voltage process, 20 volts, 40 volts bipolar process. And he taped out over 205 designs. I mean, when I say not taped out, he actually taped out and got them fabricated at SCL. And he brings in real semiconductor manufacturing experience to the panel discussion today. And, welcome to the panel discussion today, sir. And then we have Devesh Dwivedi. He's the India site leader of IP Development and Design Engineering Center at Global Foundries. So we all know that Global Foundries is one of the leading semiconductor fabs in the world. And they have a presence in India. They're doing some R&D as well as IP development here. And Mr. Devesh has 23 plus years of experience in VLSI design, industry, and leading product and IP development. We all know that IP is one of the key components for a foundry business, and he's going to give us some insight into it. And he's actually has a PhD, he's Dr. Devesh. He holds a PhD degree in electronics engineering from IIT BHU Varanasi. And he has 3 decades of strong association with IEEE. He is an IEEE senior member since 2015. He is IEEE CAS Bangalore chapter executive chair since 2020 and 21. And then we also have Suraj Rangarajan. As we know that manufacturing needs, the most advanced equipment. And Suraj Rangarajan works for one of the more leading equipment suppliers, probably the leading equipment suppliers in the world. And he works there as a India country head and CTO. And he started his career in applied materials, Santa Clara in 1997, where he held different positions ranging in the semiconductor industry, ranging from process engineering, technology, program management, and so it's nice to have you all with us today. As you all know that the manufacturing has been getting a lot of attention now, not only in India, in worldwide, and especially the announcement from the central government last year with the $10 billion incentive package, mostly targeted towards manufacturing. There is an increased attention to this segment, and to begin with, I like to have Mr. Jatana to give a little bit background about this policy, what actually it is offering to the industry, and yeah.
Hello, yeah. About the government policy which they have, few initiatives which they have taken, and last year, I think in January 2022. So it has 4 broad categories of pertaining to semiconductor manufacturing. Most important is it's a overall budget outlay, overall is around $10 billion or 76,000 crore to be given in the next 5 years to support at least 2 mega fabs, CMOS mega fabs, at a node maybe 65 or below. Then at least 2 display fabs. And then another category is of semiconductor fabs. As you know, semiconductor fab, they don't need that kind of capital outlay as a CMOS or a logic or a digital fab needs. So there can be more, even 10 to 20 kind of fabs pertaining to gallium nitride, gallium arsenide, solar. We have a lot of sun, and there are a lot of innovative multi-junction solar cells which have a efficiency of more than 40%. But we are not making, even for our satellite use, we are just importing those devices which are used in the satellite solar panels. So that is the second category. Another is the assembly and test, that OTMP or ATMP or OSAT services, because wafers, after wafers, post fab operations, testing of wafers, packaging of wafers, testing of devices, qualification of devices, and all those things. Those are, again, not that capital intensive as a CMOS fab. And then another category is of the design, fabless design. India already has made a good mark in the design, but unfortunately, we don't have our own IP. We are good at making designs if somebody gives a specification. But what we need is, we need ourselves to design the specification, to design the product, to make it. As you know, manufacturing is, today in a CMOS circuit, manufacturing is not like very tough. If you have a design, if you have an idea, you can get it fabricated, done. And then finding the market, finding the right market. So this is what in a nutshell, and the government is willing to support close to some 100 fabless design houses. I think they should have been done because they have announced the policy in the last 1 year. And this fabless design houses is the easiest part, and it doesn't require much of outlay. Government should support the design houses in terms of EDA tools in terms of at least giving 2 to 3 fabrication services outside testing packaging. It includes around, it costs around 30 to 40% of the total cost. So all those things the government needs to give to encourage various design houses. And the idea is at least in the next 3-4 years, we should have at least 4 or 5 our Indian design companies having a outlay of 5,000 crore or more.
Thank you, sir. With that, I'd like to, invite Devesh to, give a little bit introduction about Global Foundries and its operations in India. And is there any plans to help India to achieve its goals in manufacturing?
First of all, thanks, Mr. Venkata, and I'd like to extend my thanks to entire VLSI the 2023 team for giving me this opportunity. So let me start with a quick overview about the Global Foundry. So as name says, it's a true global foundries, and we are a global semiconductor manufacturing company having these fabs in the multiple locations in the US, starting from Malta in New York State, Burlington in Vermont, and then we have fabs in the Dresden in Germany, and Crolles in France, and in APAC region we have multiple fabs in the Singapore. So as I said, it's a true global foundry, considering the footprint across the globe, and we provide solution to our customers around the globe. And also, not only in the fabs, we have multiple R&D centers, design and development centers across the globe. And GF India is one of the largest design center. And not only it's the largest design center, also it's unique. Maybe I'll spend a few seconds why I am saying it's unique. So we have this GF India presence in the Bangalore, in the Manata Tech Park, and we started our operation in 2015. And in terms of the uniqueness, so the center has all the components or the teams related to the VLSI design, starting from very first, like a device physics or device modeling, to the TCAD, process design kit, to IP and design, even manufacturing support and services, although it's a remote. And we have a very strong team over here in Bangalore who do the support for the fab operation across the globe, whether being Europe or Asia Pacific or in USA. And also we have the pre and post fab validation till the silicon validation. So it's a complete ecosystem we have. That's why I'm saying it's unique, starting from your device to the complete silicon validated the IP or the products. So that's a quick overview about the Global Foundry Corporation and more specific about the Global Foundry India.
Thank you, Devesh. And with that, I request Anand to give a little bit background about TestSolve. As I understand, you are very focused, one of the leading players in test engineering, which is an integral, a key component in the manufacturing itself. Please give us some background about TestSolve and your future plans here.
Thank you very much, Venkata, for the invite and also the VLSI forum for inviting us. TestSolve. TestSolve is actually a global player. We are located in 12 countries. In India, we are in 7 different locations. We have offices and people working in US, in Canada, in Romania, Japan, Taiwan, China, Malaysia, 12 countries. We are an 18-year-old company which started in 2004. It was started by really visionary. Rajamanakam, who was our first CEO, Srinivas Chinnamili, our current CEO, and Mr. Veerapan, who is the Chief Operating Officer. 2004, I don't know if anybody in India thought about testing silicon, right? So we started with a 50,000 square foot office in Bangalore with the first tester. Testers started coming to India from all these big design houses and tech MNCs only 10, 12 years ago. But 18 years ago, we had a tester in-house in Bangalore. We had FA capability. We had FIB capability in 2004. Design houses were using FIB only in the last 6 or 7 years. So that is how we started. That was in 2004. We wanted to develop the infrastructure and for ourselves. So 2007, we found the biggest component that we needed to develop was PCB capabilities for our test equipment. So we acquired a PCB company in 2007. Today, that's the second biggest acquisition. Number of engineers working, we have about 250 people just designing load boards for testers. We did not want to make it a captive market just for us. We opened it up for any user. All tester manufacturers partner with us to build their load boards. In fact, they share the designs and they give us the early indications to what the test head and what the layout will be. So we started that, and now we are a global player even in tester hardware design. In 2009, we started a complete reliability and package qualification capability at TestSolve. Today, anybody, we have lots of test chip manufacturers, IP manufacturers, and fabless vendors who use our services for qualification of the product. We also moved from just PCB design to package substrate design. We design substrate packages for many customers. We acquired, around 2010, we acquired a IC design company to start supporting IC design, because we said we did test, next it was DFT, then it was design. So we wanted to move up the ladder. We acquired a digital semiconductor company for IC design. 2013, 2014, I think we got acquired by Hero. Hero is our owners today. 2017 or so, we acquired an analog design company, 2016, 2017, where we were able to offer full analog test services. I'm giving you all of these steps to just show how we progressed, because in 2020, we designed our first chip where we got a test spec from the customer. We designed, we got it fabricated, we tested it, and we released it to the market on a customer's behalf. So we have, in India, we just want to show we have the capability to do all of this. Not only did we design and release a production-ready chip, we also partnered with other vendors where we designed, fabricated, and also tested IPs about IP in a test chip. And we are using that IPs to develop SoC, and we will be doing the fab out of this in a month or so. In 2020, Novatelus also acquired some percentage of our company. And 2021, we opened up test floors in San Jose. So we have a test floor in San Jose. It's not the other way where US is doing it here. We did it in San Jose. Next week, we are opening a test house in Austin. So this is the capability that TestSolve developed, and we are very proud of this because we are basically an indigenous Indian company that has come up to this level. Okay, thank you very much.
Thank you, Anand. We are very impressed with your design skills and all that stuff.
Yeah.
But the topic is, can you do anything for the manufacturing? Are you planning any OSAT or move up the food chain?
Yes. When we talk about test services, right, at the test houses that I talked about,
Yeah.
these are all engineering test program development, right? So when you talk about manufacturing, We have to do a final package test program release, and we have to make the volume manufacturing happen. So we have the capability to do that. In fact, TestSolve ran a small manufacturing for prototype in Bangalore. We have that capability also. The main goal for us when we started in 2004 was to start a OSAT. In fact, we had land already bought in Perambur, and we wanted to start a OSAT for package testing.
Thank you. We want you to get back to that original plan. So with that, let's talk to Suraj, and he will give a background.
Just one, but about the chip that I talked about, if anybody wants to look at the chip that we taped out and tested and released to production, it is available in our booth. You can go look at that chip.
We'll do that. Thank you. Suraj, I will hand it over to you. You are one of the key players in this whole ecosystem.
Thank you. Thank you, Venkata, and thanks to the organizers to give us a chance to present to the design community. So the first thing I'm very happy about is we have very strong association with all these players. With SEL, a lot of our equipment is in SEL. Global Foundries, we were one of the big suppliers of equipment. And TestSolve, we were one of the early investors. Applied Ventures invested long time ago. So Applied Materials, for those who may not know, is the leading semiconductor and display equipment manufacturer. So just from a very basic perspective, when you make a chip, there are about 1,000 process steps that a chip goes through, and any electronic item, semiconductor item that you have would have gone through one of those steps with an Applied Materials equipment. Our company is 50 years old, Silicon Valley, California based, about 26 billion last year in revenue, but the industry is very R&D intensive. So we invest close to about 11% of our revenue every year in R&D. So this year we'll be investing about $2.8 billion in R&D. So that's one big aspect which will continue. Very IP rich, about 16,000 patents, and also very diverse. So we have close to about 27,000 people in 18 different countries, 90 different locations. From an India perspective, we've been in India now for 20 years, and we have 7,500 people in 6 different locations. Most of our people are in Bangalore and Whitefield, but we also have presence in Mumbai. We have a R&D facility in Mumbai where we do a lot of cutting edge development for the company. We also have a facility in Chennai, one in Delhi, one in Pune, and one in Coimbatore. And we are growing in India mostly based on the capability over here. What we do here is design, equipment design, product design, software design. The IT for the company runs out of here. And we also do a lot of leverage of the local ecosystem in a lot of new areas, especially the new digital areas, algorithms and things like that, where the company is looking at coming out with solutions. Then can we do manufacturing? So one of the reasons I moved to India 15 years ago was when Applied ventured into the solar field, right? So the first turnkey factory for Applied Materials was built in India, in Noida, in Mozambique. So manufacturing definitely can be done, and once we are able to move this forward in terms of any semiconductor manufacturing in India, Applied will be front and center of everything that happens here. Supplier development is something that we are doing right now to prepare for this to happen.
Thank you. So you are gearing up for the manufacturing in India?
Yes.
Wonderful. So let me come back to Jatanaji. So SCL has a special place in my heart. I started my career in 1985 with a 3-month internship in SCL. That's when I wore a bunny suit and went through the whole, manufacturing chain there. So we know that SEL is like founded in 1985 and was the first fab in India. When people say that there is no fab in India, kind of, I countered that. So we'll let Jatanaji give a little bit of history about SEL and see, maybe he has some views on how to make it world-class fab in the near future.
So I will start with the initial remarks from Dr. Venkata, that India has a chip manufacturing facility for the last 35 years. You see, SCL was conceived in late 70s, and first production batch came out in 1983, May 1983. It was a 5-micron CMOS 4-inch wafers. It was a TOT from AMI, American Microsystem Incorporates. AMI was a big company those days. They gave TOT to us and to Austria. So Austrian government, it was also a government company, government PSU, they named us AMS, Austrian Microsystem. So 5 micron and US also was almost, we were only 1 node behind. And in fact, initial batches were NMOS and G-line, sodium lamp, 4-inch wafers. Maximum operating speed was those days 3 megahertz, 4 megahertz. After TOT, it was planned to develop our own process R&D. And design were in those days full custom or gate arrays. The standard cell library concepts came quite later, 10, 15 years. Software was not that powerful. We used to do the layout and put it on a paper and see those metal lines are not touching each other. There were no software kind of thing in those days. But agreed, designs were also not that complex. So 2416 was a wall chip, 9495 pulse dialer. So those were the chips which we were making. We did our own 5 micron to 3 micron, 3 micron to 2.7 micron. Then in 1988, there was a big fire. Everything got burnt. The fab got burnt. We were giving some telecom chips to defense, DRDO. It was a 7-set chips. Defense told, we want those chips. You do whatever you want. So we hired AMS, Austria, because it was the same technology. Now that defense people say, you cannot give up a design to a foreign company because the Ministry of Defense will never allow. So you have to manufacture yourself there. So we were a team of 4 or 5 engineers used to be stationed there, AMS Austria, and running those batches. So I also went there and spent some time there at Austria. And while we were also developing our own lower nodes, after that 2.7 micron, 2 micron, 1.2 micron, 0.8 micron, double poly processes, E square PROM, 10 volt, 12 volt, these all processes were developed. And then after a fire, there was an inquiry and cutting the long story short, a new fab came out with the 6-inch wafer size, I think in 92, 93. We were running 0.8 micron successfully for around 9-10 years. A lot of devices were made, many devices for defense applications. PSP-1, PSP-2 for sonar, then there was a Prithvi missile, PCM encoder for there. Many, I think more than 70, 80 ASICs for critical defense applications and for space applications were made during 0.8 micron era. And then finally, it was transferred to Indian Space Research Organization, ISRO, in 2005, and we decided to upgrade to 0.18. It took 3-4 years. Presently, we have a 180 nanometer, 8-inch DUV lithography, 248 nanometer, around 8 to 10 aluminum mask stack. It's an excellent process. In-house, we have developed 5 volt, 20 volt, 24 volt, bipolar, and a lot of products have been made. And we have an installed capacity of you can say close to 1,000 wafer starts per month, total around 12,000. And it can be upgraded to around 20,000 wafer starts per month. This is the CMOS foundry, and not only the fab. There is a lot of paraphernalia which goes into the fab. There are more than 100 chemicals and gases We have a nitrogen plant, hydrogen plant, oxygen plant, DI plant, power plant, fire brigade, all those things. And we have the manpower who can run all those plants. It's not that easy. You have to 24/7, you have to run that. You have to maintain a particular clean room. We are maintaining class 1 clean room, class 10 clean room throughout the fab. It's a big fab. I think some of you might, if you get a chance, you please visit that. Excellently maintained fab. This is the CMOS. Then post-fab operations. As Tessol explained, there a lot of activity goes into it. ATE is quite expensive. Fib, failure analysis, packaging. We have a ceramic line because we were supposed to make devices for defense and military use, and their plastics are not used. SCL also has a gallium nitride G4 reactor. It's a MOCVD, and then G3 reactor, which is a gallium arsenide reactor. We don't have we are working on to develop a GaN and a gallium arsenide processes. We are working on that, basically the photodetectors on gallium arsenide and gallium nitride basically for RF applications. You see, initially, as you rightly told, we have a chip manufacturing. Only thing is, it is at a very limited scale. Ecosystem also exists at a limited scale. Only thing is, we have to optimally use that. So at least we have to demonstrate that we can fabricate 1,000 wafers. We can upgrade that plant to 2,000 wafers. So at least we have to show that we can fabricate 2,000 wafer at a reasonable yield, which is 90 to 95% is expected in that geometries. 180, and that plant can be upgraded to 90 nanometer with a very costing with a budgetary support of around 1,000 crore or so, and you can get 2,000 wafer starts per month easily at a 90 nanometer node. Only thing is, design we should have the market, we should have the product, we should have the buyer, we should have the user, and for that people are asking for a lot of reliability data and things like that, which I, like in shortage of time, I will skip those things. And
Thank you, sir. Thank you. See, I just want the whole audience know here, SCL is a hidden jewel in India. And you have done phenomenal things there, what you accomplished with whatever limited resources you have. And we hope to see SCL as a world-class foundry in the near future. Thank you. With that, I will come back to the real topic of the today. We want manufacturing to happen in India. See, there is no second guessing on that. And the central government has put $100 billion on the table. They are willing to fund up to 50% of the capital expenditure. And some of the state governments are coming forward, including Telangana government. They're saying, we're going to give you additional money, probably 10, 20%, whatever it is. With all that stuff, we still haven't seen a leading foundry in the world coming and announcing that we're going to set up a fab here. But there are a few announcements. But one of the challenges I see here is, let's say somebody wants to set up a 28 nanometer fab. Even though let's say we get all the money lined up, we still need the process technology. So where do we get it? Shall we go ahead and invest in R&D, or shall we go and partner with peoples? This is an open discussion here. I like to one of you raise your hands and start talking about it, and we will share our opinions on this. Maybe first we will go with Anant. Yeah.
See, from what I see in the industry, right, it is not just one technology you buy and then you have this running all the time. There is a very big example. National Semiconductor bought Cyrix Technologies thinking they can use their main fab to keep building x86 processors. They were very wrong, because if you want to change the speed of the frequency, your fab process has to change. And process changes are not something like you just tweak a button, it happens. There's a lot of R&D that goes behind it. When you have R&D, we are not talking only about your fab R&D. When you talk about R&D, you're talking about the physics of the devices, you're talking about mechanical engineering, your step size and things like that, where your light physics, which is lithography, all of that come into picture. So R&D and this fab technologies go hand in hand. I can't just say I buy a 28 nanometer technology and it will run always.
Your thoughts on this?
Yeah, I agree. Actually, in a process, you can have a TOT of one baseline process. There are a lot of flavors, or whatever you can say, a lot of process options. And those options have to be developed. And what is missing in India is we don't, though we have good strength in IC design, but we lack in designing a transistor. And I have seen a lot of work, a lot of PhDs going on at various academic institutions on TCAD. But TCAD is one part. Basically, it has to be done on a machine. TCAD will simply say, yeah, grow a 5,000 angstrom PR. But when you start doing it on a machine, it's not that easy. So in 180 nanometer also, there are 450 steps. Each steps have to be done very correctly. You can imagine in a node at a 45 nanometer, the number of steps will be close to some 700 or 800. Geometries are so small, there is no scope for rework. One step is wrong, your yield will be affected. So we have to, what is lacking is the manufacturing is itself a technology. Designing a transistor is another, the physics part, the mechanical part, and the engineering part, and then how running on various machines, on the process tools, then the failure analysis part. Because finally, you can say, company can sustain if you get a 90% steady yield. Otherwise, there is a cutthroat competition here. So you cannot maintain that. So unless, now coming to that point, can we have why we are not getting fab for the last 10, 15 years? My personal view is, it's very difficult for any player other than top 3 or 4, Intel, TSMC, Global, Samsung, I think that's all, to set up a fab here, make it commercially viable at below 65 or 45. And I don't think any combination of 3, 4 players will be able to make it commercially viable. This is what I think, because I have worked 30, 35 years in this industry. To make money out of it, it's very, very difficult.
But
Now,
I have a rebuttal for that. If you invite all of these companies to come and do it here, why would they have to come here? They already have facilities set up and it will be cheaper for them because here now you have to set up the infrastructure.
I agree. That is why the government is giving 50%. If Global Foundry, if they have a need to expand their capacity, expand their plant, definitely they will try in the existing plant. But here the government says, we give you 50%. You have to spend 50% only. So that is the reason. But still they are not coming. Still they are not coming. This means still, even I am spending 50%, then also it's not viable. What I mean is, how do we start? We have existing manufacturing bases in the country. KTEC is one, SCL is one, it's a beautiful plant. As you have rightly said, anybody can visit that. But we are not utilizing that. It can be, we can do 2,000 wafers at the existing node, 180. You spend 1,000 crore, you can do 90 nanometer. And now you will say, who is the buyer, who is the user? Buyers are there. There is a huge demand in DRDO, railways, your NTPC power plant, all processors in the atomic plants. We were talking to that, and Professor Kamakoti also, that processor we did at SCL, and they say you cannot put a processor which is a foreign made at a nuclear power plant. You cannot put a processor in a missile. You cannot put a processor in a satellite. So railways, we were doing a chipset for railways, huge demand. So in our core sector, we have our ISRO, we have our NAVIC. Where is the ground electronics? You don't need 20 nanometer, 24 nanometer. All government buses, you put those GPS system enabled, all trains, you put that, all your ships, boats, you put those. Those can be done. So, but people have to think, we have to demonstrate we can manufacture 2,000 wafers every month. Ecosystem will expand. Right now we are doing only 50 wafers. Government is already spending 500 crores to sustain that. And we are doing only 30, 40 wafers in a month. If we do 2,000 wafers, maybe nobody's buying, we will throw in the dustbin. Only thing, instead of 500, government has to spend 530. But we will demonstrate, look, we are manufacturing 2,000 wafers. And you can slowly and slowly, you upgrade the node, upgrade your manufacturing level. Nobody will come set up a plant for 20,000 wafers starts per month. It takes 3, 4 years, 4 years. After that, another 1, 2 years to ramp up the yield to get 90% yield. Commercial viability is doubtful. It's not that easy. Only Global Foundry, TSMC, Intel, they can make it. But a new player, no way. There are around 6 and 7 verticals. I think I can speak the whole day on that, but due to constraint of time, so I will.
So all of you guys should read a book called Chip Wars. It captures a lot of the history of semiconductors. All countries have gone through this. No country had a 28 nanometer fab come and sit and get them started, right? Everyone has to start at the ground floor. And I think I agree with you with start with what we have. If we have some manufacturing capability, get better at that, start getting out products, make it commercially viable. That's how we will need to go. I think if we keep waiting for somebody to come and build a 28 nanometer fab here, it's not going to happen.
All right.
Devesh, you want to add anything to this?
Surely. I want to, maybe I'll go a little back here. So now it's not question about setting up a semiconductor manufacturing fab here. You heard Dr. Jatana, already we have a fab, the SCL. And I heard the other presentation from Professor Nayak, the GETEC, the fab in different, I'll say, diversified technology. And Dr. Jatana said it very rightly. Now it's about in terms of the scale and the market. So our focus should be whatever the existing infrastructure is, whether it's SCL or whatever, how we can help that ecosystem in terms of bringing that scale or the market. And I'll give my perspective from the Global Foundry side. As you know that this setting up manufacturing fab is a complex process, lot of investment. And in that way, Global Foundry, as I mentioned, that has a unique presence here in India. How we can leverage that, even whatever the fab, you say SCL or whatever want to scale up, increase the capacity, the market capture. There are different ways where we can collaborate and help on that one. Let's talk about that when you're talking about the scale up. The type of the skill required in the semiconductor fab is totally different from your design house. Maybe you don't need like masters and PhDs for that. They require a lot of like technicians, the operators, maybe a diploma or maybe a Bachelor of Science, maybe a very good fit for that. But then on top of that, they require a different set of skill or training, like some sort of the basic understanding of whole the VLSI fabrication process. Hands-on experience on this starting from your wafer cleaning till the metallization. Do you have infrastructure? Do you have ecosystem for that? Suppose tomorrow we need a couple of months or year down the line, 1,000, 5,000, these such technicians. Do you have ecosystem for that? I don't think so. Maybe like we discussed about like other presentation from GETEC. They have really nice infrastructure. Can we scale that up, open up for that such type of training and such type of the hands-on exposure? And from industry side, because we are expert in that domain, we can provide the consultancy. It may be like a course development, what exactly needed, a type of course, a theory for the manufacturing test or the packaging, and also having a remote manufacturing support from here. We can share our experience and the leverage from there to train these resources for whatever the foundry, whichever comes into that. So that's my view.
Actually, sorry to interrupt you. So we're kind of talking about the skill development, as I understand, right? You know, okay, let's move forward. There are fabs are going to come. There's money on the table. Now the next challenge is going to be finding the right manpower, right? You know, we've been investing in training IT people, chip design engineers. So we already have the critical mass in there. So now the next challenge you're saying is you know, how do we find the talent to run these fabs, to operate these machines? So let's, I think Anant wanted to say something.
I just wanted to talk about the manpower.
Yeah.
Let's take example of Apple. How did they scale up? Right? Same number of, same kind of technicians, the same kind of skill set they needed. How did they scale up? I think they had a will or they wanted to do this. For all the other companies that we talked about, what is in it for them? Right? If it is an India market only that they want to capture, they are already captured it. There's nothing that they get out of coming here and developing the fab. I think mostly the nationalization where every nation wants to keep its secret to itself is hurting us. Skill set capabilities, I think we can develop. Let me give you an example. If you go back 20 years ago, 25 years ago, when one of the first IT companies or the chip companies, an analog company which set up in Bangalore, they wanted technicians to do characterization of their IPs. We didn't have, at that time there was no skill set available because none of our schools were catering for it. But TESSOL was able to develop within 3 months 150 engineers, technicians who could go help do the characterization work. So that capability I think we have in India.
So that's good. So we have extreme, okay, go ahead, sorry.
Yeah, the capability is there, but we need to build the ecosystem where this capability comes out, right?
Exactly.
If
Yeah,
a
the
pump
Apple
goes
example,
down,
right?
and you need the person to come from Singapore to fix that, your equipment is down for a week. So that ecosystem we need to build. How do you make sure that your supplier or OEMs can help with stuff and do that locally in the same time zone, right? We need to make sure that.
Just want to make a small point. If you buy any machine, if you do a comprehensive maintenance, it will cost something around 10 to 15%. When we started at SCL, the first level of maintenance, we got our engineers trained because these VLSI fab tools, they're highly sophisticated. There is minimum 3 months, 4 months training of an engineer and he only can handle and operate. It's not that anybody can go and touch that machine. It's not allowed. So first level of maintenance has to be done in-house and after that you can call visit-wise. So you can overall, you can make it a cost-wise, you can make it minimize. Another, what I find is, it's a clean room. Clean room, it's a protocol. One has to follow. And discipline is very, very important. If you sneeze or something, SCL was a government sector, there is a shift, and you go at 9, then there is a tea time, 10:30, people came out, then again go, there is a lunch time, again go. So 1.5 hours, we find the yield is drastically falling. So this is what we told. This is not possible. Clean room, they are throwaway garments. They cannot be reused. And moreover, more entry and coming, the particle count inside, you cannot maintain that. So we told a person, once he goes inside, he has to stay 5 hours there. No tea, no washroom. After that, he can go home. And we make a special provision for that. So you see, for the last 6 months, I am working in a hospital. I am attached with a surgeon and a heart surgeon. I have seen those surgeons, they stand, open heart surgery takes 10 to 12 hours and a surgeon is standing there 8 to 10 hours. Nothing of that sort. And they are 50 plus age people. So we need discipline, clean room discipline. Fab at a lower node, it's very, very particle count to maintain defect density. It will kill your dice, it will kill the reliability. So all those things are not there. Why those Singapore, Chinese, they are successful in that one, not even US. Even the same process, US yield will be different. That's why the mass manufacturing, they have shifted. And that's the reason. They're also like us, though we may be more worse than Americans. But
Jatanaji, wonderful message. The message is clear. We do have the talent force. I don't think the talent is the issue.
Talent is there.
We can make the fabs manufacturing happen, but the discipline is needed to do. It's not like tea breaks and WhatsApps and go in the fab and start using WhatsApp is not going to work. So I think in the best interest of the time, Jatanaji needs to catch a flight soon. And we all, do agree that we want to bring up manufacturing in India, right? It has to happen sooner or later. If you look at the government support, it's extremely good. We need to really thank the government. The government has come forward. It's put a very, liberal and generous package on the table. And as an industry, we have to step up and make things happen. And whether it's, fabs or OSATs or, if not the cutting edge fabs, whether, we talked to, Tushar gave an excellent presentation. A GAN fab has a huge, huge requirement, opportunity in India. A gallium arsenide fab has a, it can not only serve the strategic reasons in India, worldwide also. So with that, I want each of you to give a quick summary to the whole audience here and the whole industry. What can we do to make things happen in India today?
Sure, maybe I'll start with that. So you heard about that, the stage, and also I'm really also very excited to hear about the recent announcement from the central government, state government, and all the agencies. The very positive way they are pushing forward in this direction. And you know that maybe 20, 25 years back when we started on the design, software, services side, that was the start. And today we have the state of art in terms of the world class. Name any domain or area. And I'm very positive that same will happen in the second other half, like the manufacturing, testing on that side. And also, as we heard about that some of the recent announcement, either from government side or some of the consortium, I think now our focus should be to, with the existing infrastructure, industry available here in India, how we can work together and make them successful to deliver that result. We discussed about one example about the manpower, skill development. And if I talk about the GF perspective, I said that unique presence GF has. Even we discussed about the gallium nitride technology. GF is one of the premier in terms of this technology offering. Maybe there is opportunity for partnership, collaboration on that one. And also, hope you heard about some of the initiative from Global Foundry side. One is called GF Lab. This is the worldwide initiative. Now we are expanding it in India. And last 2 weeks, we covered at least 7 IITs and NITs. We are going to all the IITs, NITs, tier 2 colleges. Yesterday, we had a discussion with the IIT Hyderabad, Triple IIT Hyderabad, and before that, we had with the BITS Hyderabad. And today, because I am here, I'm planning to meet the Triple IIT Hyderabad in terms of this GF Lab opportunity. It's not just only like internship or faculty engagement, it's to the next level in terms of the partnership, the technology collaboration, services, consultancy, whatever. So I think in summary, my message will be lot of the positive, I'll say the push from government, industry, and academia side. Now we have to come together and work, collaborate, and help to make this successful.
Thank you. Anand?
I think I look at it as 3 different steps. First of all, we have to make the world accept made in India as something that will happen. Otherwise, I can create all this.
They're already accepting our mobile phones.
Until Apple came, they did not. Okay. Right? So the world has to accept us. Otherwise, whatever we manufacture, we'll have to keep with ourselves, like how Dr. Jarani said, we'll have to throw away the wafers that we are building. Second, we have the talent, but none of the talent is being utilized inside of India. We talked about all the fab, we talked about all design houses, everything. You go out there and see it's us Indians who are running most of it. But somehow we are not able to keep the talent in here and build the talent here. So the academia may need to step in here and try to develop things which we can give to the world. Today we all talked about getting technology from outside. What are we developing and giving to the world? Because once we do that, then there is value for it. Otherwise, we are also a consumer. See, when Global Foundry or TSMC or somebody comes and sets a fab, they are going to take the profits away from them, from us, right? We are just a consumer. They are happy to set it up for us. But we have to have our own indigenous stuff. be done here. And again, now fab, all of us said, is going to be a more expensive thing. We may have to take a step back. Let's go do OSATs, just package testing. For package testing, don't go buy the package technology. Create the package technology here with the universities that you're working on, different package material, things like that. Do some research and give it to the world where they'll also come and buy technology from us. And that is when I think we will get there. Just buying technology will not.
Good message, Anant. One quick summary from you, Jatanaji.
Yeah, I think all of us know about Sam Petroda's contribution to the telecommunication area 20 years back. So here, at the ministry level, particularly the MIT level, quick decisions are needed. CMOS logic, I understand, huge money, it might take time, but it should not take much time on fabless design houses. What is there in giving free EDA tools, giving 3-4 batch fabrications outside, and all those things, and compound semiconductor fabs. They should quickly decide within 2-3 months. And then use existing infrastructure. You see, when there was a fire in '88, most of the Singapore fabs, ST Micro, Micron fab, First Silicon fab, they are running by ex-SCL chaps. Many of them will be willing to come back.
Yes.
And they are the people who have worked at the process development at a lower nodes. You bring at least 3-4 people, good chaps, give the keys of SCL to them, run them, and ensure product penetration. Some assure product market. We have automotives as Tata's, Mahindras, definitely they will be willing. So it is possible, but government has to policy decisions, making policies, they have to implement that at ground level, which is not happening. Making good announcements will not work. Use the existing thing first.
Thank you, sir.
Sure. I agree with all the things that people have said. One thing that I would add to all of this is pick areas where there is India demand. Display, right? Television, we are the third or fourth biggest consumer of TV. Everything is important. It's easy to make that local with some small steps. Communications, where there is a lot of inflection happening. How do we make localization of manufacturing a part of that? Auto, there is again inflection happening over there. How can electronic semiconductor be part of our plan to that? So that way, we should have some pull, because I agree that if we build it and you don't have application, you don't have a buyer, this will not be sustainable.
Thank you, and let me do a quick summary. We are at the end of this thing, and I think the message is clear. The government has come forward. They put a very liberal, generous package on the table. The industry has to step up. The 3 nanometer, 5 nanometer fabs can wait. There are other things we can do. Compound semiconductor fabs can happen. OSATs can happen. And at the same time, we also need to focus on fabless startups ecosystem. The government also has a DLI scheme, extremely innovative scheme, extremely thought out scheme, very well thought out scheme, and we should also start having product companies designing chips. Initially, they can be to TSMC, but they can slowly transition to whether SCL Foundry or some other foundry that comes up in India. With that, please give a big round of applause to all the panel members here. It's been a great discussion. Timing is right for India. This decade has to, be for India. Thank you all. And with that, I invite. Next, I invite Subhash. Srini, can you come next? Anant ji, can you please come on the stage and Anant for Anand. With that,
Thank you, everyone. Thank you for that very engaging panel discussion. With that, we conclude the morning sessions. The track presentations will begin at 2:30 p.m. There will be 4 sessions running in parallel. Please review the agenda and proceed to the corresponding venue for the session.